Hi everyone! Now that we've got a pretty good handle going on solving exponential and log equations, I want to go back to some of the applications that we started with for exponential functions and answer some of the solving questions that we didn't have the tools for yet. So this is an example where we have a drug that's eliminated from the body through urine, and we know that 20% of the drug is eliminated every 3 hours after the drug is administered. So the start of this is just like what we did with exponential functions. We need to set up a formula that represents this. So I'm going to say A is the amount of drug, and T is the time since administered. So we are looking for an A of T formula, and we are not actually told an initial amount in this one. So I'm just going to use that subscript notation to represent initial amount. So A sub 0 represents the initial amount of whatever variable A represents. We know that 20% of the drug is being eliminated, which means we will need to multiply by 0.8, find 80% of what we started with to figure out what we have after one elimination period. If this 20% reduction was happening every hour, this would be a 0.8 to the t, but it's happening every 3 hours. So we actually need to slow that down, which means we're going to do t over 3. So this is as much as I can do for setting up a model with the information I was given. Part B asks us to estimate the half-life of the drug, and this is again one of those amazing things about exponential functions. The half-life is the amount of time it takes for the drug, in this case, to cut in half. That does not depend on how much you started with. So we are fine to go ahead and start working on this, even with that A sub 0 still in the equation. If we want to know when we have half of what we started with, that's half of A sub 0. A sub 0 represents whatever we started with. So this is my setup, and it might concern you at first to have an extra variable in the problem, but maybe you can spot now that that's going to drop out really easily. We can just divide out the A sub 0. You do want to be careful about dividing out your variable, but we're solving for t, so dividing out an A sub 0 should not cause us any problems. So now I have 1/2 equals 0.8 to the t over 3. And this is a kind of standard looking exponential equation. So I'm going to solve by using logs. If you use a log base 0.8, it will cancel out really nicely, but I actually have different advice for word problems. I know that in the end, I'm going to want to plug this into a calculator and get a decimal answer that I can hopefully make a little more sense of. So I would recommend using a common log or a natural log, assuming that's what your calculator has available. Most calculators will have both of those, but not necessarily an option to put in any other bases. So let's go ahead and use natural log this time. If I take the natural log of both sides, I end up being able to pull that exponent down to the front. So I get a t over 3 natural log of 0.8. And then I can multiply by 3 to get rid of the 3. And I can divide by the natural log of 0.8 to get rid of that, and all I will be left with is the t. And this is nicely ready to plug into a calculator. I ended up getting roughly 9.3189 if you want 4 decimal places. I in general will be fine with 2, but for my open math you might need a couple more. This was in hours. So the half-life of the drug is about 9.3189 hours, and this problem does have a second part, just to kind of refresh this. Once we know the half-life, we're supposed to write the equation in another way based on that information. So we already have this A naught times 0.8 to the t over 3 formula. And that's a good formula. I'm not claiming I'm going to write a better one. In fact, this new one will have some rounding because it's going to use this 9.3189. But just to remember how we would write an equation based on a half-life, we would say we have some initial amount, we still don't know it, and that gets cut in half every 9.3189 hours. So remember, we can use half-life or doubling time in the same way we can use percent increase or decrease. Okay, and then last question, if the initial dose is 10 milligrams, when will there be 1 milligram remaining? And we could technically use either formula. Since we weren't told, I would definitely choose the top one because I rounded in the half-life formula. So I'm going back to that A naught times 0.8 to the t over 3. And I can actually do a little bit better. I was told now that I started with 10 milligrams, and I'm being asked to find when I'm down to 1 milligram. So this is asking me to set my equation equal to 1. I am trying to solve for t. There's only one of them, so this is going to be a reverse order of operations type solve problem. The first thing that I need to get rid of is the 10, and it's attached by multiplication, so I will divide. So I get 1/10 equals 0.8 to the t over 3. And then once again, I need to use a log to get t out of the exponent. So basically the step would be I need to get rid of the 0.8 right now. You can use a log 0.8 and do that. But again, if you're thinking ahead, I would say use a log base 10 or a natural log. I am going to use the log base 0.8 though, just so that I can remind you of what you do if you don't think ahead. So I will use the log base 0.8, and that is 1/10 still. And the log base 0.8 of 0.8 to the t over 3. On the left-hand side, I can't really cancel anything, so I'll just keep that as is. On the right-hand side, the log base 0.8 and the exponential base 0.8 cancel, and I'm just left with the t over 3. And then my last step will just be to multiply by 3, so I get t equals 3 times the log base 0.8 of 1/10, at which point, if you weren't thinking about it ahead of time, you're maybe starting to think about, oh, I need to plug this into a calculator, and my calculator probably doesn't have a log base 0.8 option. So what you're going to need to do at this point is use the change of base formula. And maybe you'll prefer this way and just do that always because it's not that hard, but a lot of people will forget their change of base formula. So it can be nice just to deal with this ahead of time. This time let's use a common log. So I'm going to change my base to common log, which means I can just go ahead and make this log of 1/10, change to the new base, but then you correct by dividing by the new log of the old base. So the new log is common log and the old base is 0.8. And this is what I head to my calculator with, although I would say you should be able to do this one in your head. That's saying what power of 10 gives me 1/10, and the answer is -1. So if you spot that, I really just need to plug -3 over the log of 0.8 into my calculator. And I got roughly 30.9566. And that again will be hours. So to go from 10 milligrams down to 1 milligram, we need just about 31 hours. All right, so same setup as we did when we started exponential, but we now have the tools to solve algebraically.